or not? Did you do them in section 5? Now there's ones that are fairly easy, and that's the ones where you just have an e to the minus ax and an e to the minus by for the density functions, and they're both only for positive. But other parts that become complicated. If we're done with section 5, and you will get quizzed on this and section 7, so I want to be sure you know that. The next thing we're going to do is section 3-7 in the book. So I'm going to use my usual business here. And guys aren't sitting next to each other this time. All right. So here in section 7, I'm going to tell you, and I put this up last night, but now we're talking about using something that he terms a characteristic function. Don't use this characteristic function. It's basically the negative of the Fourier transform. It's silly to use this thing because you already know Fourier transform and Laplace transforms, all right? So I'm going to put down a few rules. This is for section 3-7. So for section 3-7, the first thing is if you have functions that really are only defined for z, x, y greater than 0, and they're less than, for anything less than 0, then use the Laplace transforms. And if they exist, from, call it x, y, z, greater than minus infinity, less than infinity, then use Fourier transforms. Now I'll show you what I mean by that. And first of all, whenever you take a look at a convolution problem, if you have an f of x, and it's given, first of all, let me do it this way. If you have z equal to x plus y, we're assuming we have this. We've been doing these things. And if x and y are statistically independent, so here at this point they have to be statistically independent too. Now, we've said this many times. Then what you can do, you have an f of x and an f of y, and we're looking for an f of z, and they're statistically independent. Remember, z is x plus y. Then you can say that f of z is equal to f of x. Argument can be z or anything, convolved with f of y. Now, that simply means you can use convolution in the most simple sense to do it, but convolution can be a pain. And I think everybody agrees that it can, there's usually 3 or 4 different regions where you have to think about how you do the integrations, because these come down to integrations, right? So if that's the case, then you can use the Laplace transform. This is assuming that these two functions are only valid for y and x greater than 0, and there's 0 below that. You all with me, class? This is critical for this. So you can use the Laplace transform. You can get f of s, or fz of s, equal to fx of s simply times fy of s. And that's nice, because we can use partial fraction expansions if we want the inverse transforms. And we've done this already. We did this, I think, in section 3-4 and 3-5. Do you all remember doing this? So that should be, by this time, pretty clear, and you should be familiar with it. Now, the next part is, what if you want moments? And this is important. I'm using a Fourier the Laplace transform here, but we can do for Fourier too. If you want moments of anything, for instance, if you wanted the expected value of z, which would be z bar, Then you take a look at the definition of the Fourier transform. Try to clean that board a little. And the definition of Fourier transform is actually equal to the integral from 0 to infinity. This is the one side that you were taught of really f of either x or y or whatever it is, but it's f, and this next variable is a dummy variable, so you can put f of z if you want, e to the minus sz dz. Now, the definition you're familiar with is f of t, e to the minus st dt. But you're going to integrate through dt so it never appears in the answer. You all with me, class? It doesn't matter if you use z, x, y. It's just a variable that is of no consequence. And I might as well put down here, if you have f of omega, the Fourier transform, then the integration goes from minus infinity to infinity of whatever this is, call it f of z, and it would be e to the minus j omega z dz. You're used to seeing t there. I'm using z on purpose so you get familiar with that. It doesn't matter what the variable is. It can be a function of time or space or anything else, or an abstract dimension, but you have to understand this concept. When we have this, if we take a look at f of s for a second, and we take a derivative of f of s with respect to s, then what we end up getting is an integral from 0 to infinity of s with a minus sign times f of z e to the minus sz dz. I'm just going to stop here. Y'all follow me on this, class? What I'm really pointing out is, by definition, this is the definition of f of s, and I take a derivative with respect to s. The only thing that comes out there is a minus s inside the integration. Y'all with me? Now, if I look at this right here, or I'm sorry, minus z, gosh, minus z, my bad, because I'm taking a derivative with respect to s. Does everybody follow me on this? Now, there's minus sc, take a derivative with respect to s, the minus z comes out in front. If you look at this, by definition, and you let s go to 0, you'll notice that that is the definition of the moment. Second moment's negative. This becomes, if that goes to 0, it becomes minus the integral of z, or whatever value you want here, of f of z dz, and that's from 0 to infinity, and that is the definition of the mean value of z. Does everybody follow me on this? How many do? Are you with me? It's fairly straightforward and clear, but until you do it a few times, you can fumble this pretty easily. Now, you'll notice there's a minus sign, so after you take the derivative, you have to multiply by a minus sign before you evaluate what that is. Correct, class? Y'all with me to get the moment? Now, if you want the second moment, and these are things that are important, or the third or fourth, or whatever, if I take another derivative of this with respect to s, I'm just going to get a z squared, and the minus sign goes away. How many see this? That would be the second moment. Everybody see that? The third moment, you take another derivative with respect to s, and you'll see there will be a z cubed here, but what you're really doing is taking derivatives of the transform, f of s, with respect to s, as many times as you want. Y'all with me? With me on that? Now, that's for the functions if they exist for positive, 0 and positive values of x, y, and z. If you have values that exist, like from minus infinity, infinity, then you have to use the Fourier transform. All right? Same exact concept. If you take a derivative of this with respect to omega, you see you get a minus j z out in front. Y'all see this, class? It's just like this one, only there's a j there. If you evaluate that function after you take a derivative and let omega go to 0 and multiply by j, then you can get the moment that way. You all with me? We're gonna apply this to some problems. How many tried these problems? I just need an honest thing for section 7. I don't think you did because I posted it last night and I don't think you had time, but some of you may have. Has anybody even looked at that section? I mentioned this earlier. Do you remember me talking about the derivatives with respect to f of s to get the modes? Well, let's do some of these problems now because I need the whole board here. I think it's going to be valuable to see it applied. And by the way, in the book, he uses a characteristic function. Now, the reason I really dislike it is because there are no tables for this. Basically, this thing is created. I'm sure there's a benefit to it, but instead of having this function right here, he puts a plus j omega, or plus ju. Doesn't even use omega. You with me? All right, it will be a transform, but now you don't have tables to go back and forth. It's irritating. He even mentions it's almost identical to the Fourier, so why not use the Fourier? It's much easier, in my opinion, because you're familiar with Fourier transform. Fourier transform pairs, Laplace transform pairs, you're going to use all through your undergrad, from your juniors, right? Juniors and senior level, when you get into comm, and I can't imagine the other courses, depends what your emphasis is, you get this all the time. And it really doesn't go away. It's so important to understand and appreciate this. Technically speaking, you should see circuit concepts in all the classes. I think we've talked about a few of them, right, in this class, but it's not like every problem has it. But you have to know that. Signals and systems concepts you'll see continually along with circuits concepts. And depending on the area you go into, digital, where you get binary decision making, will be in any kind of digital signal processing or digital image processing or anything like that. And a lot of stuff that has to do with, I think, Wi-Fi. Are there any wireless engineers in here? That major basically died, but they do a lot of that stuff too. They need it. Okay, now getting back to this. Now I'm going to do problem 3-7.1. This is fairly straightforward. Can you give that to me?
A random variable x, has a probability density function of the form f of x equals e to the negative x times u of x. And an independent random variable y has a PDF of f of y is 3e to the negative 3y times
Go ahead.
u of y.
And z equals x plus y, I think.
Yes.
All right, so this is in essence the simplest possible problem you could get. What do they ask for first? Do they ask for f of z?
The PDF of z.
All right, so it's a probability density function. Really, it's f of z. Ask yourself this: if I gave you a quiz right now based on what I put down, how would you go about solving that using a concept? Hint: the concept is Laplace transforms. So what do you know that is equal to? Well, first it's equal to f of x of z convolved with f of y of z. You can just have any, the variable here has to be the variable here. That's the only comment, right? And then if we use transform theory, what do? That's convolution in one domain. It becomes f of z of s equals, the capital just implies the s domain, f of x of s times f of y of s, right? Everybody follow me? Now I'll just put this up here for everybody's sake, but this is something I expect you to know. Once you write that down, put an underscore, this transform pair you must know. So if you have e to the minus 8, it doesn't matter what the variable is, I'll use x here, u of x, and you want the transform, call this the f of x or f of t, whatever you want. It transforms to f of s here equal to 1 over a plus s. Now how many remember that one? If you had like e to the minus at, u of t, you all know that transform, right? You've got to know this one. Matter of fact, it is almost unthinkable that you don't when we go forward, because this is going to be used so much. I'll go a step further. If you just have u of x, that transforms to simply 1 over s. You can see if you make a here 0, you get e to the 0, which is 1, you get u of x, and the transform of that would be 1 over s. Everybody follow the reasoning behind it? Let me do it. Well, that's good for now. All right. Everybody with me? So when we have these functions right here, if I have e to the minus x u of x, then what does that transform as?
1 over 1 plus s.
Does everybody see that? The coefficient of x is 1 up here. So it's going to be 1 over s plus 1. And what does 3e to the minus 3x, or 3y, it doesn't matter, 3y u of y transform as? Someone else.
3 over s plus 3.
Right. 3 over s plus 3. First, does everybody see that? Simple transforms. Now, if we have that, the next thing we do is this. We say, therefore, my fz of s, I may have done this exact problem, but I don't remember if it's the same exact problem. It seems to be. Now it's just going to be 1 over s plus 1 times 3 over s plus 3. Everybody get that? Multiplication, or convolution in the time or in the x domain implies multiplication of the two functions in the s domain, the transforms of the functions. You agree with that, everyone? Okay, keep going. At this point, we have to use partial fraction expansion. One of the things that I always try to tell people, remember this thing. It's not just when you're an undergraduate, you get through something, I'm done with it, I'm not going to see it again. The reason with the in electrical and computer engineering courses, you're going to see usually those concepts over and over and over and over again. Circuit concepts, signals and systems, random concepts. You see this continually as you get in the upper level courses, and it's unavoidable. And on the job market, it depends on what you do. If you're in sales, maybe not. But I always say this, mechanical engineers that needed to sell a car, right? But to build one, you need one. And it's the same thing with the real world. If you're out there selling Dell computers, you don't have to be an engineer, you know. But if you're building them, you have to know these concepts. So back to this thing, this goes over to A over s plus 1 plus b over s plus 3. Those are the poles. Poles are values. These are called single poles because if we had s plus 1 squared, that would be a double pole. If we had s plus 1 cubed, that basically has three things you'd have to expand. A 1 over s plus 1, a 1 over s plus 1 squared, and a 1 over s plus 1 cubed to do this correctly. But anyway, for this one, in the most simple sense, how do, and I think I did talk about this, how do you define A? How do you find A? In the back, yeah. How do I find the value of A?
You do the partial fraction.
I've done it already.
Yeah. You put the s times 3, it'd be 3 equal to a.
Well, actually, I'd cover up this, wouldn't I? Because I'd multiply both sides by s plus 1. I want
Yeah, that's basically, you multiply both sides by s plus 1 and s plus 3.
And then you would evaluate s at minus 1, right?
Yeah.
Because that's where this pole occurs at minus 1, right? Does everybody know what I'm doing? Just recall this, just one time. If I multiply everything by s plus 1, I get 3, you don't have to write this down, equal to a plus b times s plus 1 over s plus 3. Now, we evaluate that at the pole, we evaluate this at s equals minus 1, and you'll notice what happens. At minus 1, this goes to 0 times b, it goes away. So I just evaluate this, and this would be equal to A equals to 3 over 2. Y'all follow me? 3/2. How many remember this? Hopefully everybody recalls this. You may not have done it in a while, but you recall it, right? Okay. So A is equal to 3/2 over S plus 1. And then how do I get B?
Multiply out S plus 3.
Yeah, I cover up. That's what I do, right? Cover up that S plus 3, because I'm going to multiply both sides by that, right? And then I evaluate the remainder at S equals minus 3. At S equals minus 3, what do I get? Well, I get 3 over minus 3 plus 1, or 3 over minus 2, or minus 3/2. I'll give you a tip about this. If you notice this, if you look at the poles, S plus 1, S plus 3, if you really want to get A and B quickly, you can mess with this. These are simple poles, two simple functions, right? Basic simple poles. You can just say, find that pole by the cover-up method. This will be minus that. It's always true. Can you all see that, class? So B is just minus A, and that's always the case. Now, this is my F of Z of S. So how do I get my F of Z of Z? I have to do what? I have to find, I have to find the inverse Fourier, or inverse Laplace transform. Do you all agree? What is it for the first one?
E to the negative Z.
It's really 3/2 first, you're right? And then it's E to the minus 1 times Z, or just minus Z times U of Z, right? Now, somebody else, what is this one gonna be?
Minus 3/2 e to the minus 3z times u of z.
And times U of Z. Or, in general, F of Z is going to be 3/2, and then you're going to have E to the minus Z minus E to the minus 3Z U of Z. And if you plot that, F of Z here versus Z, remember this starts only for Z greater than 0. If it was less than 0, if you had values of F of X or F of Y that were for negative values of Y and Z non-zero, I mean, it would be non-zero, then you can't do this. And it would look like what? It would look something like this. Let's see. Something like that, right? Got one last question for anybody. How do I find that value right there, the peak value? That would be the most probable value. Right. I take a derivative of that with respect to Z, right? And what do? Set it equal to 0, solve for Z, and then go back here into this equation and see what the value is for F of Z. Correct, class? Okay, that's F of Z. What else does it ask for?
That's it.
Well, I'm going to ask for something. I posted on the homework. Okay. I'm going to do this. Get rid of this. That's 3/2. This is minus 3/2. And now I want Z bar, the expected value of Z. Form that question in your mind. Make sure you ask yourself how to do it. Because if you're wondering, that's when you usually remember things. If you don't wonder and you're just being fed information. Okay, think about it. How do I get that? Yeah, I mean, you could go back to the F of Z multiplied by Z, right? And then integrate from 0 to infinity. But that's a pain. That's my version of that. It's a pain. It's just not fun. Or take the derivative with respect to
S.
right? So if I take the derivative of this with respect to S, what do I get? I get 3/2, that's gonna be in front of both of these, right? Derivative of the first one, that's really what? This is s plus 1 to the minus 1, right? So it'd be minus, right, 1 over s plus 1 squared. Y'all follow me what I'm doing here? This is gonna be the derivative. This is gonna be the derivative of f of z of s with respect to s. And what about this one? Then it's gonna be plus, now look, this is like s plus 3 to the minus 1, correct? Oh, if you take a derivative, you get a minus sign, right? But there was already a minus right there. So it becomes plus, and then it's gonna be 1 over s plus 3 squared. So now I've got this, what's the next thing I have to do?
Set s equals 0.
Yeah, I need to do that. So we're gonna go ahead and make s equals 0. But there's one last thing.
Make it negative.
Multiply it by negative, because this is the first derivative, so multiply it by negative. This becomes positive and this becomes negative. And then we evaluate that at s equals 0. Does everybody follow the reasoning? The logic is important to see. What is that equal to? Well, if s goes to 0, really what I have is 3/2, and then I have 1 over 1, or 1, and then I have minus 1 over, and that would be 3 squared downstairs, or 9. So really, it's going to be 3/2 times, and this would be 8/9, unless I've done the math wrong. And that's going to be simply 4/3. Does everybody agree with that? Now you can go with your calculators. You go ahead and check that. You're gonna. Would you do me a favor? Remember the f of z we had? We had f of z equal to. Let's see here. 3/2 e to the minus z minus e to the minus 3z u of z, right? If you multiply that by z, that function, can you do the integration on yours or not? I know you're using a calculator. I don't know if you're trying. The reason I'm showing you this is because that integration may be a real bear on your calculators. I don't know, but remember, you're going to have to take this function and multiply it by z and integrate it from 0 to infinity. Just see how much trouble that is. I can do it on MathCAD almost instantly, but plugging things in calculus. Oh, by the way, Anna Grace, you need to talk to Christian, because he'll show you where he made a mistake. He
Okay.
knew exactly what it was. This
Okay.
is a different class.
Thank you.
It's a pain. And this is the part of the course, I hate to say it, where some people just fall off the cliff, so you gotta keep up with
My calculator overflows.
it. It really is.
Yeah, it has trouble evaluating things in infinity.
Well, you don't have to put infinity, just put like,
I put like 9 to the 10 to the 9th.
no, how about 10 to the 3rd would be enough. Did you get anything, Elijah?
Invalid implied multiply.
Anybody else? The only,
1.33.
4/3. Now, here's my point. On your calculators, when you get some of these problems, if you try to go the old-fashioned route, multiplying that by z, or z squared, y'all follow me on this? Or z cubed, third moment, you go nuts. It's so much easier to take derivatives of the Fourier transform with respect to s, 1, 2, or 3 times, and every time it's odd, you gotta multiply by a negative sign. If it's even, you don't. You all with me, class? Are you good with that? I'm saying this for a reason, because I'm trying to give you a heads up of the problems you'll see coming on the final, the next quiz possibly. I don't think next quiz, well, maybe. I think about it. Yeah, that could be a problem. Y'all have 36, who has 36s? Or what do we call it, Inspire, is that what it is? Isn't that 36, it isn't? I don't know the number. What do you have?
I have the TI 84.
Who has 84s? Okay. 80. I'm gonna level with you. Could you do that integration if you multiply by z, or you could? Okay, good. And he did it, but you have to put, instead of infinity, you have to put like a large number in there.
Yeah.
I don't even know if your calculators have the ability to put infinity in there, unless it's symbolic.
Can symbolically, but not really.
Okay, anyway, y'all with me on this class? And suppose I ask you this, like on a quiz, like on a quiz, like on a quiz. Suppose I wanted the second moment, just the mean squared value of z. What do?
Second derivative.
See this? Now actually, at this point, you take another derivative, but you have to multiply by minus, correct? If you took another derivative, I don't think your calculators can do this. Don't do this right now. Take another derivative. Now this becomes 1 over s plus 1 cubed. Y'all with me on this? Then this is going to be 1 over s plus 3 cubed. Y'all with me? The signs will change. That'll be negative, that'll be positive. And when you do it and evaluate at s equals 0, you'll get the third, or you get the second moment. Y'all with me? Now, if I wanted the variance, just hear me. Let's assume we have the second moment by evaluating the derivative of this twice with respect to s, setting s equal to 0, and solving for that. Then, if I wanted the variance, what would I do, Jose?
The mean square value minus the expected value squared.
Y'all hear that? That's right. You would take z squared bar minus z bar squared to get that. Now, that's 3 easy things to understand, but apply them and do them to make sure you don't have any uncertainty about how to do it. And the biggest problem is these derivatives. You have to be attentive. You can mess up a minus sign, easy to get a minus answer. And by the way, if z is only valid for positive values of z, in other words, f of z is 0 below there, for any negative values of z, then the mean value, the mean squared, any other moment has to be positive. Do y'all follow me? It cannot be negative. I just want to make sure you're clear about that. Okay, next.
So the first part is find the characteristic function of
We're
a.
not going to do characteristic. Let me just write this down first. We're going to use Fourier transform or Laplace transform because they ultimately want either the f of z or they want the mean or mean squared or something like that. All right, go ahead, Elijah.
So should I skip that problem? There's a part B that said use the characteristic function.
We're going to use the other one, but I mean, give me the problem.
Is it Gaussian random variable?
This is a tricky one. I'm not going to ask you this, but I'm going to go through it quickly. You can just watch. You don't need to write it down unless you want. All right, so they give you f, is it a z or what? F of a?
It doesn't get.
All right, so it's this, 1 over the square root of 2 pi, here, sigma. And it's exp to the minus z squared over 2 sigma squared. What they're doing is saying the mean value is 0. All right, now what do they want? And that, by the way, is defined for positive and negative values, or, sorry, x. He's just giving you a density function, a Gaussian density function. Go ahead. He wants the characteristic function, right?
Yes.
All right, we don't use characteristic function, we use Fourier transform. This is tricky. Matter of fact, let me do this. No, this is fine. So if I want the characteristic function is almost identical to the Fourier transform, but the characteristic function of this, I'm going to use omega, not u, is equal to the integral of minus infinity to infinity of f of x e to the minus j omega x dx. In other words, it is, the characteristic function would have a plus there, if you look in the notes I posted there, and instead of w for small omega, it would have u. That's it. This is easier to use. You're familiar with that. Everybody should be, right? I had to look this up. Now, If I take that and put it in here, try to do that integration, even your calculators can do it. Does anybody remember the trick for this? It's kind of a cool trick. The way you do it is you take a derivative of that with respect to x. Now just watch. So you take a derivative of f of x with respect to x, and that gives you 1 over the square root of 2 pi sigma. And then when you take a derivative of, and by the way, you would get the derivative of this is going to be minus 2x, and then it's going to be over 2 sigma squared times e to the minus x squared over 2 sigma squared, right there. And if you look at this, now, do y'all follow me? I took a derivative of that just with respect to x. Follow me? Watch. This 1 over square root of 2 pi sigma, and this is f of x. Do you see this? In other words, what I'm about to circle, that is f of x. So I can rewrite this as the derivative of f of x with respect to x is equal to, and this would be minus x over sigma squared times f of x, right? Now this is some property. Do y'all remember doing something like this back in the day? I bet you 1 or 2 of you remember this problem. This is a classic problem, by the way, because you can't get the Fourier transform, at least in any way, shape, or form that's easy by evaluating this. There's a lot of those kind of problems. I could show you a bunch, right? At least one more. If you want to say it, just see me out. So I get this, and now you may remember, if you have, and I'll use t, f of t goes to f of omega. Then if I have df dt, that goes to j omega f of omega, right? Do you remember that property? And if you have t times f of t here, what that implies, multiplication in one domain is derivative in another domain is going to be the derivative of f of omega with respect to omega with a, typically it's going to be a j downstairs or a minus j. Do you remember these things? These are tricky little properties, but it's almost the same for s. For s, this would be just s f of s, and down here, this is going to be minus f derivative of f with respect to s instead of a j there. Y'all with me, class? Okay, so come over here. I'm going to try to just do this real quick. So I have df dx really instead of dt. So this is going to be j omega f of omega here. But I don't think he expected you to do it this level. I don't know how he did it in solutions literature. On this side, you get minus, it's really going to be minus 1 over sigma squared here. And then we have x times f of x, or t times f of t. So then I get that 1 over j here, and I get df of omega d omega. Now you can see this is getting already a little irritating. Correct, class? You don't have to know how to do this exactly. I'm just showing you this because I can see something like this coming up in the future where you, at least you should have this in your mind. If you can't see the Fourier transform or Laplace transform direct, think about taking a derivative of the function you've got in the domain, either x, y, or z, and seeing if you can solve, taking the derivative of the transform and see if you can get it. First in the actual domain like I did, then you have to take the transform of that. So here's the thing I'm going to say. I have a j. I'm going to multiply both sides by j. J times j is what? Minus 1, right? Do y'all agree with that? It gets rid of this minus. And now I have this. I'm going to just, so I have, this is 1 over sigma squared, and I have that. So I have omega, f of omega equals 1 over sigma squared, df of omega, d omega. And here's what I really do at this point. Now I go ahead and I'm going to multiply everything by d omega, and I get omega, d omega on this side, and I'll multiply by sigma squared over here too, but it doesn't matter where. And then I get equal to df of omega over f of omega. Can you all see, just by doing cross multiplication, you get that? Take a look on the bottom, multiply both sides by d omega. That gives me omega d omega over here. Multiply by sigma squared, get sigma squared there. Then on that side, you get d of f of omega over f of omega. Can you all see this, class? Elijah, I mean, you might not be able to read my writing far back. Everybody good with this? All right, now, if I want to solve this thing I can leave out in front, it doesn't matter, but now you have to integrate this. Believe it or not, the integration goes from 0 to omega on this one. If you ask me why it's over that range, I don't have a really good answer. But it has to do with the defining, how you define the value of the transform. It's not to infinity, and basically you can't go to infinity because this answer has to be a function of omega. Y'all with me? So it starts at 0, goes to actually omega, and technically I should do this. Okay, on this side, you're going to get, look, this is going to be omega squared over 2. From 0 to omega, you get sigma squared, omega squared over 2. And on this side, when you do an integral, that's like an integral of 1 over x dx. You get natural log. Y'all with me? So now you get the natural log on this side. Natural log of f of omega. And if you have a log x equal to something, and you want what x is equal to, you take every e to that power on both sides. And now you get e to the minus sigma squared omega squared over 2 is equal to f of omega. And lo and behold, that's the transform pair. That's a pain in the butt. So that means this transforms into e to the minus sigma squared omega squared over 2. Can you confirm that, by the way, the answers? I don't remember. I didn't look at the solutions, I just found them.
That's what they have.
It's a pain. Does he do it that way or not? You gotta get the transform. It's a pain in the butt. You probably can have transform pairs of this typically, right?
Yeah, he didn't do it the exact same question.
Did he do a did he do an integral?
It looks like he did it using the characteristic.
All right, it's still ridiculous. I mean, what I'm saying is, this integration, he may have done it that way, but it's a mess. It really is. I think he probably cheated a little bit of it. Because you can't get a form of that that's easily solvable. You have to do expansion. Anyway, so this is the transform of this. And that's what we really need is this transform. Now, what does he ask after that? Sorry, it's
Using a characteristic function,
forget character, Fourier transform.
verify the result for the nth central moment of a
Okay.
Gaussian.
What he's really saying is, remember, if you have a Gaussian distribution with 0 mean, you found this, that the actual nth moment, call it x to the n, the expected value of x to the n. That's assuming it's got a 0 mean, right? Of a Gaussian was equal to what? 1 times 3 times 5 times dot, dot, dot. Basically, times n minus 1 of sigma to the n. Do you remember that? Where sigma was the standard deviation, right? So if we're gonna do that, let's at least do one real quick, because I spent a lot of time on this, so we're gonna do it. Here's the actual value here of the transform. take a derivative of that with respect to omega. What do you get? If I take a derivative of f of omega with respect to omega, I get what? And remember, we gotta evaluate this at omega equals 0, right? Can you see you're going to get equal to 2 right there, and it's going to be omega, right? And then it's going to be times sigma squared over 2, and then it's going to be that e to the minus, and this whole business here, which is sigma squared, omega squared over 2, but you have to evaluate this at omega equals 0. That goes away. That would be the first moment, and you have to evaluate it at 0, which is, when omega is 0, that's 0, right? Second moment would be what? Well, you would take that value here, right? And divide, and you take another derivative. Guess what you get? You get a sigma squared coming out in front. And you're going to get 2 terms, but at the end of the day, you'll see this recursive relationship. I'm sure he has that in the solutions bank, but he's just taking derivatives. Can you see it? Here's what's nice about this. Fourier transform or the characteristic function has no j, which is nice. Can you all see that? Do you remember the Fourier transform of Gaussian? No? Well, the one thing that's imperative to realize is this has a Gaussian distribution in time, and this has a Gaussian distribution in frequency. But the key thing to note here is the faster this changes in time, or in other words, how the duration of this gets shorter and shorter, that would mean that sigma squared here gets smaller and smaller. In the actual frequency domain, this gets broader and broader. And that's one of the things that they try to teach you is if you have any pulse function in time, the narrower it is in terms of its duration, and the frequency domain, it's broader. And in the limit, when you get an impulse function in the frequency domain, it looks like a constant up and down the frequency band. Y'all with me, class? Something to at least glean from this. Okay, enough of that. Next problem. Wait, let me.
Yeah.
We're going to get that. By the way, I don't expect you to be able to do a transform like that. But that type of approach to some things, and I'll give you more information as you need it, is something you do have to be aware of and able to do. There's something called duality too you can use. I want to do that right now. I want to get through this, and then I want to do chapter 4. We're going to do at least one more, which is 3.
3-7.3.
Yeah.
It gives the characteristic function of the Bernoulli distribution.
Wait. All right, so this would be I'm going to show it in terms of Fourier transform, all right? So they give you, I'm going to call it of omega. And here, is it 1 first?
Yes.
1 minus p. P is the probability of the event occurring. This is called the Bernoulli. What did he call it? The Bernoulli what?
Distribution.
Just distribution. Remember, did you remember where we had a function early on where you had n possible events and you wanted to take, n possible events, you want to take k of them. There's a probability of success of p, probability of failure of 1 minus p. Y'all remember that? How many different ways you can take, like, 3 things if you have 5 total. In other words, the different permutations. But this is the characteristic function, and I'm going to make it the Fourier transform of that. And then it's going to be, I think this is plus e to the j, and this would be u, right?
Yes, it's also p.
Sorry. It's plus p times e to the ju, right?
Yes.
All right, make it minus j omega because u and omega are related by a minus sign. All right, now say you got that and think of it as the Fourier transform. I could give you something like this. It would be easy to do if you understood. What do they want?
The mean value of the Bernoulli random variable.
how do we get the mean value? Let's just think. You can prove it, by the way, with the Bernoulli distribution stuff. What was the concept with the Laplace? We took a derivative and set the value of s equal to 0. Here you take a derivative and set the value of omega equal to 0. Instead of multiplying by minus 1, like you did with, here it's a j, minus j. You all with me, class? So what happens? If I take a derivative of this with respect to omega, now these two go away and I get what? P, right? And I get minus j, correct? And then I get e to the minus j omega. And then I have to, just multiply this by j. And if I multiply this by j, well, j times j is minus 1. With a minus 1, it gets rid of this. And then I evaluate it at omega equals 0. And that means this is simply p. And that should be the actual mean value of, was it z in this one, or?
U. Oh wait, no, that's, he didn't give.
Well, this would be the mean value of whatever the variable is in the, with the density function given. I can use x bar, this is, sorry, just x bar, and that's p. Is that the answer? Or not? I'm sure it is.
You said it's just P? Yes.
That's the first part. Now, the difference, and I'm sorry if I'm going a little fast, the difference between using the Laplace transform, you multiply by minus s. For this, you multiply by j. All right, because j times j would be a minus 1, and you have a minus sign. Typically, we'd have to get rid of that minus in the Laplace domain. Because remember, for Laplace transform, s is j omega plus sigma. If you got rid of the sigma, you'd find the exact same operation would happen, basically. Y'all with me? Just try these things, you'll see it. And by the way, it has to be positive. You can't have a minus p as an expected value. It can't be negative. Y'all with me? All right, what else?
I was wondering, why did you have the J on the left side?
When I took a look at this right here, if you take a derivative, you're going to get a j out in front of minus j, right? Now you have to multiply that by j to get rid of it. Normally it's like this. If we wanted the mean value, and remember this has possible values for all possible omega, right? When we do Laplace, it's only for 0 to positive infinity for s, right? So here, if we want this value, it's going to be, you take the derivative of, and he uses, I'm calling it the Fourier transform of omega, right here, d omega. Then you multiply it by j. In his book, he'll have a minus j, because he has the characteristic function, not this. Multiplied by j, and then evaluate this at omega equals 0, and you will get the right answer. You have to play with this a little bit, you'll see it. And remember, if we did it the other way, we multiply by minus s, right? Can I still do it though? I mean, if you, let's see. I think you can do that substitution. What's the next part of that one, Elijah?
The mean square value of
All right, I'm going to just ask the obvious. If we get the mean value, basically you're going to get the minus j out in front. If I want mean squared, I have to take another derivative. Do you agree with this, class? Now, in fairness, I probably am not going to give you a problem where I use the term characteristic function. I will use terms you're familiar with, Fourier or Laplace transform, if I give you the actual transform. And I'll ask you to deduce what the mean is or anything. Here's a tip. The value of the mean for any function from 0 to infinity has to be positive. That way, if you have a negative value, you'll know it's going to be wrong. Can you all follow me on this? Is there another part to that?
The third central moment.
All right, we're going to forego that because it's just one more derivative. Follow me on this one, class? And then these are central moments. Remember, for all the stuff we did before, central moments assume the mean is 0. Real quick, well, actually, what's the next problem? And then I'm going to ask you, please do this, but go ahead.
It's two statistically independent random variables, x and y, have PDFs given by x is 5e to the negative 5x times u of x, and y is 2e to the negative 2y times u to the y.
All right, both positive, hear that? F of x and f of y are simple exponentials. Think of the first problem we did. We know we can do Laplace transforms of both and multiply them to get f of z if z is equal to x plus y, is it?
It is
Okay, what do they ask for?
the probability density function of z.
How many know how to do that? If you don't, please see somebody or talk to me after class. That's two transforms. You multiply together, do partial fraction expansion, then go back to the actual z domain, and you will see it is just like the first problem. What's the next thing they ask for?
The first and second moments.
Just derivatives of that function of f of s with respect to s one time and then 2 times. But for the odd values of derivatives, you multiply by a minus 1. For even, you don't. Can you all follow me, class? Okay, now I want to go to something in Dr. Denny's notes, and because I've got about 10 minutes, or 12 minutes, but I want to do this, and I'm telling you the reason for this. His notes are excellent about what we're about to get into in chapter 4. Something else I got to tell you about this. This is going to be something where you got to be attentive, really attentive about this stuff. Do you need to go? Oh.
I see.
No, I mean stand up if you need to. I have a problem sometimes. I need to get up because my back hurts and stuff. Stretch. I don't care if you get up. But here's the notes. Now these are PowerPoints that Dr. Denny created, but they're excellent for this stuff. I gotta tell you one thing. He really did an outstanding job of highlighting what's important in really important actually in this this chapter. There's a lot of information in here. I'm not saying it's not useful, but it's not necessary. Not yet, but in a second I'll tell you get the lights. Hold on. It's coming up. All right. Hit the center on. I'm going to go through this, and this, by the way, these PowerPoints are there. This is chapter 4. And now we're going to talk about statistics, and this is very important for things like elections. Do you know how they say poll numbers indicate so-and-so is a 50-point advantage, and these points are out of like basically the person's going to win, but they're wrong. Y'all know what I'm talking about? How many do? You have to have been around for elections. Right? What the poll is based on is what they call a fair sampling of the population. In other words, the sample is proportional in ID ideas and everything of the general population. Most of the time that is completely wrong. They try to figure out ways to deal with the uncertain, which is really just guess. That's how they do it. So let me get to the point. And he even talks about public opinion polls here. It's kind of fun, but I see manufacturing as the really pertinent thing, because some of you in here are likely going to work for industries that create an enormous amount of VLSI chips and stuff like this, or components, and they can't test every one. So what they do is, if they have batches of like 10,000, they may test 100 of those. And they're going to assume that if there are defects percentage-wise in that they reflect the defects in the overall sample. That's the idea. Should make sense to you, right? Okay. Maybe not so. So they say if you just have something where this shows you if you got 1,000 resistors and the mean value, the true mean is 1,200, or supposedly is 1,200, and they're just showing you the possible values that they have. He created that just saying if that's the number of resistors and these are the values, you see that they're more or less centered around 1,200, but there's a variance. You can see it's all over the place. So the first thing is, what is the mean of these resistors? If you select 3 randomly. Now the key thing here is random. I don't know which resistors I'm going to take, but if I take the mean of any 3, that's a random variable. Just think about it. Say you take 3 one time, you get a mean. Take 3 again, you get a different mean. There's one thing about the mean you get with the number of resistors for a small sample. The more of those you take, the closer it gets to the true mean. That should make sense. If you take them all, you got to get the true mean. Okay? And he just gives an example here. If you select 3 resistors, now you get a mean. That's anytime you have a small letter in the notes or in the text that I put up, that means an absolute value that is non-random. If you get a large value of X, then it's a random variable, or it is a true mean, one of the two. So how many resistors do we need to sample to ensure that the mean is within 1 ohm of the true mean? This gets interesting. So now we define some things. I'm going to try to go through here quickly. Capital X is just a random variable representing the population, and X, capital X of I, is a sample taken from the population. Obviously, the small x's are a particular value of X, a particular sample from the population, and then whenever you get bars, you know that that's mean value. You all know how to calculate a mean. Just add up all the values, divide by the number. When you have that, if that's the true mean, it is not a random variable. We know what the sample is. That doesn't change if you have a total number of resistors. That's the true mean. The theoretical mean is a random variable, but it gets a little interesting. Then there's the actual sample mean of small x. So we're going to cut to the chase here. Now, if you think about this, we're going to have capital N values of resistors, but we're randomly selecting any 3. In other words, these 3 can vary. More or less, you can select 3 one time, 3 another time, 3, and you're going to get this value of the mean. Can you all understand that this now is a random variable? So here's where the statistics come in. You have to be attentive here. It says it's a random variable. The mean of these randomly selected samples is a random variable. You can see it's going to get closer and closer to the true mean in the limit, because you select all of them. And then we pick another 3 resistors, and we're going to get a different value. The first value of the mean was 1219, and the next mean is 1196. Both just values of this randomly selected 3 samples that mean to that. here's where it gets good. So he's showing you the sample mean of 3 randomly selected values. You don't have to write this down, just appreciate it. And one thing he's trying to show you, doesn't come across clear, is this is getting closer and closer to 1200, which is the true mean. Okay, this is just redefining the means by definition. Anytime you have a capital X bar with a hat, it means the sample's random mean. And when you get a true X bar, it means the sample's true mean. That sample's mean. And now, on average, now he's going to start using this term unbiased and biased estimate. I'll explain this in a bit, but there are some oddities that happen where actually a sample's variance is not, you know how if you have a sample, you have capital X bar hat, all right? That is going to be the mean of the sample. Well, it's varying, right? So there's a variance of the sample's mean, and that variance, we can find the variance of the variance. This gets interesting, it's not in this section. Just bear with me on this one. So what is the expected value of the sample mean? You can go through the gymnastics on this. The expected value of the sample, which is defined as this. This is a random variable. And it comes out that the actual expected value of the sample mean is a true mean, which is nice. It would make sense it is, if you think about this. As a matter of fact, that's by definition what it is. It has to be. So what the question is, and this is good, we're assuming, and this is kind of an oddity, if we really know the sample mean, and we really know the sample's standard deviation, we can calculate how many resistors we need to select in order to get the sample mean within a certain percentage of the true mean. Just figure that out in your mind. The question I always have is, if you know the true mean and you know the standard deviation, true standard, why are you doing any sampling at all? That should be the logical thing that you think about. Why are we doing this? We're doing this for an academic reason, but it's going to show you how the concept works. Then we'll do the reverse, that if we do the sampling, we can infer what the real mean is between certain values. And that's sort of what polling does. It polls a group of people, and it does an inverse problem where it figures out the mean and the standard deviation. This comes later. All right, I'm going to cut to the chase here. Basically, on average, the sample mean equals the true mean. How much the sample mean vary about the true mean? That is called the variance. Now, just watch this. So, a variance of anything, has to do with the squared value. And remember what I said earlier. If you have the mean squared value minus the mean value squared, that is the variance. Are you with me, class? All right, so the expected value of, you'll notice he takes the definition of the random variable of the mean, that's this, just adding them up, because x of I is a random variable now, and that right there is random. Squaring it, you get these terms, you're going to get two sets of summations, and you get all this crap. Let me get down to the basics. After all this is done, you can look at this later, you end up getting this, and this is the important thing. You see this variance of x squared minus x bar squared over n is equal to this. And I think he does it right here. So let me put this down. I want to do it this way. This one you can write down. Remember, the variance of, now this is the sample's mean. This is the variance of the sample mean is equal to sigma squared. This is the true variance over n. And this is true for n much, much less than capital N. Now, what it means is you're sampling a small portion of the total number. And I'll show you how this works, or how it's applied. 1 minute over. I'm gonna try to get this done without going too fast, but just bear with me on this one, because it's important to see this. All right, the real way I like to understand things is by applying it to problems. Lots of different problems with different, all the different possibilities. So here, if we look at this resistor problem, okay, he's going to give us a true variance of 50 squared, or 2,500. So the question at this point is, who cares about sampling? But again, go along with the joke, because we have to do this problem first to get to the inverse of this, where we just look at samples and we infer what the actual value is of the mean. So we get the variance is equal to sigma squared over n. We're only sampling 3. Can you follow me, class? So we've got 2,500 over 3, sigma squared over n. We get this value. And then we see that if we take a look at this, standard deviation is just the square root of this. He's just showing you the larger the number of samples, the smaller the standard deviation gets. But I'm going to have to tell you this. What I put up there is true for sampling without replacement, or where you're sampling a small number of the total number, like say 100 out of 10,000. But if you've got something that's small in size and you're sampling it, and you're not replacing that resistor that you sampled, it's called sampling without replacement, then this would be the variance, where n is the number of samples and small n is the sample size. And I might add, you better, I don't have time today to do this, but look at this example. And I'm not going to quiz you on this Friday, but I do appreciate if you look at this example and do the problems I give you, just using the 2 formulas that I showed you. And you'll be surprised how much you glean from that, because we're going to move into variance of the sample, variance of the variance of the sample. And I have to do that. But Friday's quizzes aren't going to do it. The quiz is going to be related to section 3-5 and 3-7, some of the problems we did today. Y'all with me on this class? And you need to know how to